Welcome everyone to the Advanced Plasma Power webinar. We're just about to get started. The title of the webinar is Renewable Sources of Hydrogen for the Chemical Industry. And just to give you a little background into Advanced Plasma Power, they're a world leader in advanced waste-to-energy and fuels technology using our patented Gasplasma technology. We're delighted to have Rolf Stein, CEO of APP, and Simon Jones presenting this webinar. Before we get started, just a few housekeeping notes we need to cover. To reduce background noise, we have muted everybody, but if you do have a question during the webinar, please submit it to me, Charlotte, listed on the participants list, and submit it any time during the chat facility. And then Simon and Rolf will answer them at the end of the presentation. So I will return at the end of the presentation and questions to inform you how we will share information after the call. So now I'd like to hand over to Simon Jones to begin.
Good morning everybody, and thank you very much for joining our call this morning. I'm first of all going to give you an introduction to APP, and then we'll go on to the subject we're going to be discussing this morning. Advanced Plasma Power was set up in 2005 to develop and sell gas plasma technology that we'll be discussing today. Gas plasma is a process that is designed to take waste materials like municipal waste and waste from commerce and industry and convert it into useful fuels and energy. In the past, this kind of waste has either been dumped into landfill or incinerated. Incineration does generate some power, but it is not very efficient and results in significant amount of ash, which still needs to be disposed of. Our gas plasma technology means that virtually 100% of municipal waste can be diverted from landfill, and there are virtually no emissions. Our pilot plant here in Swindon has been running since 2008 and allows us to test various types of waste for our customers, and it also demonstrates how effective and reliable the process is. Almost all industrial hydrogen used today is produced by reforming natural gas. Now, despite there being vast natural gas reserves around the world, there are many uncertainties over supply and prices. This is particularly the case for those countries with little or no natural gas reserves of their own. For this reason, it's important that industrial users of natural gas and hydrogen explore alternative sources of gas with more predictable futures. In the next few slides, we're going to look a little bit deeper at the factors affecting the supply of natural gas. Up to 95% of current hydrogen production is derived from fossil fuels, and most of this is from the reforming of natural gas. Natural gas is also used in the industry for direct heat, as well as being a precursor for other important chemical compounds such as ammonia for fertilizer and the processing of crude oil. With the increasing demands for electricity and the reduction of use of nuclear power in some countries, natural gas is also seen as the quickest, cheapest and cleanest way of building new power stations. As can be seen from this graph, the cost of natural gas in the US has fluctuated wildly in the last 10 years. At some point in the last 10 years, it has been nearly 160% of the price in the year 2000. The current lower price on this graph is probably more to do with the economic slowdown and the production of shale gas than the long-term declining trend. Most experts in fact expect that the global cost of natural gas is going to go up, at least in the short and medium terms. The price of natural gas can also vary greatly between different countries and regions, depending on whether a country has gas reserves or access to reliable reserves that can be transported economically. With so many key sectors depending on natural gas, such as petrochemicals, the manufacturing industry, power generation, agriculture, and of course ourselves to heat our own homes, the demand for gas is likely to stay high for the foreseeable future. Now, whilst the world as a whole has plenty of gas reserves, they are not all economically accessible. And as can be seen on this slide, the vast majority of proven conventional gas reserves are controlled by a small number of regions. Some of these regions have countries that could be considered to have volatile political structures, and there could be major changes in the next 15 years or so in the landscape. These changes could add further uncertainty to the market and risk the companies that depend on gas. There are also potentially a lot of unconventional reserves like shale gas, but it is likely to be 5 years or more before many of these can be developed. Transporting gas to consumers is also a challenge. Pipelines are the most efficient method, but they can take a long time to build and only have a certain capacity. As has been seen over the last few years, pipelines can also be turned off from time to time. When the tap was turned off to the Ukraine a few years ago, there was a lot of panic in the gas markets and a lot of uncertainty. At the moment in Europe, several planned pipelines have been put on hold or cancelled altogether. I apologise for the poor quality of this map, but it shows the current major pipelines as well as some of the planned ones that have been cancelled. There are many experts in the field predicting gas supplies in Western Europe could be very, very tight over the next 10 years or so. There are many people on this call outside of Europe, so you will know if this kind of situation is also affecting your region. The other method of transportation is by ship, but this is quite expensive and there is a long lead time on new terminals. This will also lead to an upward pressure generally on gas prices. The other factor to consider is emission trading and carbon credits. The future effect of emissions trading and carbon taxes are also difficult to predict. Europe has probably the most comprehensive emissions trading system at the moment, but other countries are also developing them, and the United Nations also has a scheme. In Europe, the current allowances are higher than they were expected to be due to the economic slowdown, and so the scheme has not bitten as hard as we might have expected. Not yet, anyway. The system is currently being reviewed, and there are various predictions on how the price of carbon credits will develop over the next decade or so. This chart is used by the UK government as their best guess, and if it's right, the price could be around €20 within 10 years or so. €20 is actually what the EU would like the tab to be now, so it's likely to be their minimum target and their target for legislation. In terms of gas being used for power generation, this would mean an increase of around about 20%, or about €4 per megawatt. For chemical production, like ammonia, for example, it could actually be much more. All of these factors mean that the supply and pricing of gas over the next decade or so is highly unpredictable. Any prudent company that depends on natural gas as a source of heating or raw material should explore alternative, less volatile sources to reduce its exposure to these risks. Now, I'm now going to hand over to Rolf, and Rolf is going to go into the background of the waste management.
Thank you, Simon. Set against the pressures in relation to natural gas is a further global challenge in relation to waste management, which we face around the world. As population increases, consumption increases through a burgeoning middle class, our waste problem is getting bigger. Set against this is a decline in the acceptability of landfill as a solution to our waste management challenges, incineration becoming increasingly unpopular and challenging to obtain planning permissions and building consents, whilst at the same time our natural resources are in decline. Any waste management solution, modern waste management solution, needs to embrace the shift from waste management to resource management, which is where our solution can play an important role. A second major challenge is the need to decarbonize and to produce energy and fuel sources from lower carbon sources in a cost-effective way. Our Gasplasma process is the combination of established and proven process equipment configured in a novel and new way. First of all, we feed prepared feedstock, which has had recyclates removed, in particular metals, both ferrous and non-ferrous, glass, and also dense plastics, which have a value as a recyclate, to leave a residual feedstock with a relatively high biomass content. This is fed into a conventional fluidized bed gasifier, where the gasifier effectively is the workhorse in transforming this solid material into a crude or dirty syngas containing relatively elevated levels of condensable tars. This gas, as well as the residue from the gasification process, the ash, are passed into a secondary plasma stage, which is none other than a refractory lined vessel with an electric arc which is struck from a graphite electrode to the base of the vessel to create a very clean source of heat, but also of UV light. This plasma stage is very effective at cracking the tars in the organics in the syngas, as well as vitrifying or melting the inorganic component within the ash into a solid material which we have called Plasmarok. I'll say a little bit more about Plasmarok in the subsequent slides. The cracked syngas, comprising mainly hydrogen, carbon monoxide and some carbon dioxide from the gasification stage, are passed then into conventional wet and dry gas cleaning equipment to remove acid gas constituents, before then exiting the cleaning and cooling process to be utilized as a source of energy for power generation, or for alternative uses such as shifting to pure hydrogen, or partially shifting and converting into substitute natural gas. These are all options that we are currently working on, and as well as further options such as the production of liquid biofuels. This next slide really encapsulates very nicely the effect of the plasma cracking stage. The sampling points on the left of the slide is of the gas exiting the gasifier. These are samples actually taken from our plant in Swindon, but can be samples from any gasifier operating on a waste feedstock. You can see relatively elevated levels. Here we have measured for toluene, hexane and phenol, and we also measure for benzene, which is a particularly refractory organic. The levels are reasonably elevated. If this gas were, for instance, fed into a gas engine or turbine, the equipment would foul very quickly. By passing it through the plasma treatment stage, you can see on the right-hand side of the slide, we have again sampled for toluene, hexane and phenol, and the levels of those species are barely detectable. This makes our gas plasma process an ideal solution for producing a clean syngas from waste feedstocks. I'll hand back over to Simon to talk about the further downstream processing of the gas.
Thank you, Rolf. This slide shows a comparison between the production of syngas compared to natural gas. As Rolf said, after cooling the syngas, it is then cleaned using standard dry filters and wet scrubbing to remove any remaining fine particulates, acidic gases and heavy metal vapors. Then the syngas is ready to be used. This slide also gives an insight into the basic economics of the process. Natural gas is effectively free of charge while it is in the ground, but then has cost associated with it as it is removed from the ground and transported to where it is to be consumed. The raw material for the gas plasma process often has a negative cost. In other words, the plant would be paid to take it. This of course varies according to the location of the plant and the type of waste, but it can be a very significant part of the cost effectiveness of the plant as a whole, as we will explore later. Also, the concept is that the plant will be located very close to the point of consumption. Ideally, transport would be via a very short pipeline, so transport costs are eliminated. This slide shows the typical composition of the syngas. It will vary a little depending on the type of waste being processed. However, in all cases, hydrogen and carbon monoxide form the largest constituents. The ratio is roughly 1:1, depending on the nature of the waste stream. This can be changed using the water-gas shift reaction to increase the hydrogen content. There may also be a very small amount of sulfur compounds, chlorine compounds, and ammonia present, but these can be cleaned further depending on the requirements of the downstream process. This slide compares our syngas with natural gas. It is slightly denser, but still lighter than air. Syngas has a lower CV than natural gas, so for direct heating applications you need more syngas and more burners. Although syngas has a lower CV than natural gas, the Gasplasma process has been designed to maximise the CV, and we are confident that our syngas retains the highest CV of any waste-to-syngas process. An example of this is that we use oxygen and steam in our fluid bed gasifier. This dramatically reduces the volume of nitrogen in the syngas compared to the gasifiers that just use air. And it probably goes without saying that, like natural gas, combustion results in CO2 and H2O. Moving to the carbon footprint, burning our syngas has a lower carbon footprint than natural gas. This is in addition to the carbon benefits of diverting waste from landfill, which are considerable. Many landfills are emitting methane, which, as you will know, attracts a very high carbon tax in some countries. In fact, within the European emissions trading scheme, carbon emissions from waste are actually carbon tax-free. This slide shows some typical uses for our syngas. Simpler chemicals like hydrogen, methanol and methane can be produced using the water-gas shift reaction and then catalytic conversion in the case of methanol and methane. Fischer-Tropsch can be used to produce more complex hydrocarbons such as diesel and kerosene. And ethanol can be produced by using the fermentation processes that are now becoming available. And of course, energy can be generated either by direct combustion or by running a gas engine or turbine directly on the syngas, as Rolf mentioned earlier. In fact, we're the only company that we're aware of who has demonstrated the operation of a gas engine on our syngas over a prolonged period. We've been doing this for the last 5 years here in Swindon, and this demonstrates how clean our syngas is. Syngas is a good alternative for natural gas where a process requires direct heating. The energy density is lower, as I mentioned earlier, and this needs to be considered when specifying burners. However, there are potentially large savings on the carbon footprint. The direct heating application will depend on local economies and local economics. If there are reasonable gate fees for waste disposal, and the local cost of gas is relatively high, or there are green incentives available, it would certainly be worth exploring the potential for using syngas in your process. If your process requires hydrogen, then syngas is likely to be a highly cost-effective and sustainable source for your power plant, for your plant rather. First of all, there is no need for the high energy cost associated with steam reformation. The raw material cost of producing syngas will depend on local conditions, as I mentioned a moment ago, and the cost or negative cost of the feedstock. However, we can say that the cost of converting syngas to hydrogen is definitely lower than the cost of converting natural gas into hydrogen. This means that in many cases the overall cost of using a gas plasma plant to generate hydrogen will be significantly lower and more predictable than the cost of using natural gas and steam reformation. Even more so if you consider the carbon credit benefits. We're not suggesting that you should get all of your hydrogen this way, but if a substantial proportion came from alternative sources such as waste materials, your company's exposure to the fluctuations of the gas market could be dramatically reduced. I'm now going to hand over to Rolf, who's going to talk a little bit more about the technology.
Thank you, Simon. As I mentioned at the outset, we have combined established technology, equipment that has been proven the world over, many thousand hours of operation, millions of hours of operation. Gasification, around 500 or so gasifiers operating globally, with a syngas capacity of in excess of 800 million normal meters cubed per day, or 70,000 megawatt hours thermal per annum. The majority of those gasifiers operate on coal and petroleum, but a growing number on biomass and waste feedstocks. They have been operating for decades with high availability. In our own particular case, we have selected a fluidized bed system supplied by Autotech USA, formerly Energy Products of Idaho, with over 100 fluidized bed systems operating globally. Our plasma system is supplied by global plasma leader Tetronics, our sister company, established nearly 50 years ago and having supplied in the order of 80 systems globally. Again, these have been operating for many decades on a variety of different feedstocks for different applications. The image on the bottom right is of a system vitrifying incinerator bottom ash and fly ash in Japan, a capacity of around 40,000 tons per year. The systems have very high availability and operate in the most demanding environments, including in steel mills, stainless steel plant systems, amongst others. Tetronics is the exclusive supplier of the plasma system to APP for the Gasplasma process. The next slide really summarizes the closed loop nature of our proposition. As I mentioned, the first step after waste collection, of course, which we are not involved in, is to separate recyclable materials from the waste feedstock to produce a pre-prepared fuel with a relatively high biomass content. The recyclates, in particular the metals, the glass and dense plastics, are recycled back into industry and the economy to create a circular economy. The residual material is then processed through our Gasplasma system, which I described earlier and is set out again here with all the process steps to produce at stage 4 a cool, clean syngas for a variety of applications, including on-site power generation through engines, turbines, or fuel cells as this technology develops, either high-temperature fuel cells or alkaline fuel cells, hydrogen fuel cells, but also the production of biofuels, of hydrogen, of substitute natural gas, of liquid biofuels, as Simon set out earlier. We're in fact working currently on a project with National Grid in the United Kingdom to demonstrate the production of biosubstitute natural gas from our syngas for grid injection, for injection into the gas grid. The other important point to note from a corporate responsibility perspective is that this represents, this circular proposition is an ideal solution. I said that I'd talk a little bit about the other output. We focused on, obviously, on the syngas, which is the main point for discussion today. But the solid output, which we have called Plasmarok, is a vitrified material, an aluminosilicate in the main. It is extremely strong and hard, quite dense, very low leaching. As you can see from this graph, extensive leachate testing was undertaken on the material. The red or magenta bars are the acceptable levels of leachate for inert landfill. Not that we would landfill this material, but that is often seen as the standard by which the effect on human health is judged. The blue, barely detectable bars are the leachate results from our testing, the values, and in many cases several orders of magnitude below the inert waste acceptance criteria. In the UK, we have gone through the protocol to establish this material as a product with the Environment Agency and not a waste. We therefore have no wastes resulting from our process, with the exception of a very small amount of gas cleaning residues, which in themselves can also be further processed. The raw materials for our process on the input side can be all manner of different organic materials, from municipal waste to commercial, industrial waste, more hazardous materials such as sludges, as well as waste products from biomass production and agriculture. Municipal solid waste and industrial waste will usually be at a negative cost, which means that you will be paid, your plant will be paid to take the material on a long-term supply agreement basis. We have undertaken some analysis of the forward price curve for various fuels, and Simon has talked very eloquently about the pressures on natural gas pricing as we move forward, with a general prediction of an increasing price over time. The trend in relation to other fuels is similar, in particular oil. Coal is perhaps as the most abundant fossil fuel in a slightly different category, but is of course an extremely high carbon emitter. Forecasting pricing isn't easy. We have taken a combination of the best available forecasts for this slide, and it shows the anticipated cost per megawatt hour. What this does demonstrate is that while all fuel types are likely to rise in cost over the next few years, it is very unlikely indeed that waste materials will need to be paid for. This underpins our claim that using a gas plasma plant to produce hydrogen, or syngas, is probably the most stable and predictable source available.
Thank you, Rolf, and that brings us to the end of the presentation today. Thank you very much for your attention. For reasons of confidentiality, there's a limit to how much we can say in a broadcast webinar like this. And we've only been able to give you a brief overview of the process, its applications, and the technicalities, and particularly the outputs. If you'd like any further information, please feel free to contact me after this webinar, and you can see my contact details there on the screen in front of you.
Thanks everyone for attending, and especially to Simon and Rolf for taking the time to share such useful information today. And if you have any further questions or require more information, then please contact Simon via the email address shown here. Many thanks for attending again, and we will be in touch very soon. Thank you.